Okay, so as mentioned in the email this video is attached to, a uniform beam of weight 196 newtons and a length of 1 meter is attached to a hinge on the outside wall of a restaurant. A cord is attached at the center of the beam and is attached to the wall, making an angle of 30 degrees with the beam. The cord keeps the beam perpendicular to the wall. If the breaking tension of the cord is 620 newtons, how large can the mass of the sign be without breaking the cord? Well, we know the beam is in equilibrium, and both the net force and the net torque acting on it must be zero. So to find the maximum weight of the sign, I let the tension in the cord have its maximum value of 620 newtons, and we don't know the force exerted by the hinge on the beam. So what I did was choose an axis of rotation through the hinge. Then the force exerted by the hinge of the beam has a zero lever arm and does not enter the torque equation. But before I did anything else, I drew a diagram to show each force acting on the beam, and then chose my rotation axis. And that's this first drawing up here and everything. And then from there I drew each force vector starting at its point of application. So I was able to find the torque, and I did this by finding the lever arm or by finding the perpendicular force component, and then the distance from the axis of the point of application. And again, my first drawing up here is just the sign hanging outside of the restaurant. And the second one is the forces acting on the beam. And then finally, the third one is after I found the components of the tension in the cord. And now using this information, we can see that the gravitational force of the beam can be taken to act at the midpoint of the beam since it is in uniform. And then the force due to the cord has a perpendicular component, and that's why I use this equation here. For the perpendicular force is equal to 620 newtons times the sine of 30 degrees is all equal to 310 newtons. And now the two gravitational forces tend to rotate the beam clockwise, while the tension in the cord tends to rotate the beam counterclockwise. So the net torque must be equal to zero again. Now, in finding that, I use this equation here of 1 meter times mg is equal to 0.50 m times 310 newtons minus 196 newtons. And now, because I know this, I was able to solve for the unknown mass, which is the capital M. And that was using the equation here of 0.50 m times 310 newtons minus 196 newtons, divided by 1 meter times 9.8 newtons per kilogram. And I get that the maximum weight of the mass has to be 5.8 kilograms, or it'll break the cord.